Hey, welcome everyone to deploying egress traffic controls in production environment. It's a bit of a mouthful, the title, but I promise you we've got a valuable presentation ahead. I'm Graham Zuloff. I'm a Principal Solutions Architect with AWS, and I'm joined here with the real all-stars, Houston and Kevin. And we'll kick things off here. We're gonna have a quick overview here of our agenda. We're going to talk about why do we even need egress controls. Also a primer on AWS Network Firewall. It's going to play a key part in our discussion today, so if you're not familiar with the service itself, don't worry. We'll get you up to speed real quick. And then we're going to hand off to Houston. He's going to talk about Robinhood's journey in adopting Network Firewall, but you want to pay close attention to how they phased in that adoption to their production environment. And then Kevin is going to dive deep into the real meat of the presentation, the level 300 details that you're probably here for. That's the deployment and the implementation of the service. So why do we need egress controls? Well, example of the log4j exploit that was recently in the wild. A difficult one to mitigate, but part of that exploit, log4j, after a host is attacked, is it has to reach back out to download a payload and then execute that code. Egress controls can mitigate and protect against that sort of attack. Also, many command and control frameworks depend on phoning home, outbound communication in their attack. So egress controls help mitigate and protect against that exploit. A recent report from Cisco Talos said that 66% of ransomware attacks used command and control, specifically Cobalt Strike. And so egress controls is an important way to protect against that attack. AWS Network Firewall, what is it? It's AWS's managed service that makes it easy to deploy network protection for your VPCs. It's easy to set up, it's just a few clicks. It has fine-grained access control where you can create rules or import rules in open source formats. And also, it allows you to set policy and then apply that across all of your VPCs and accounts. It's built for the cloud. What does that mean? It scales. So as your traffic increases, the performance and the ability of Network Firewall keeps up with that. Supports hundreds of thousands of connections, has HA built in. You don't need to size instances or patching or anything like that. Again, flexible rule engine. And it has compatibility with a number of formats that are common. So how do you use Network Firewall? Simple, log into the VPC portion of the AWS console. You create a new firewall there. You can then create rules, associate those with policies, deploy an endpoint, and then you're protected. Then you can also use Network Firewall Manager or AWS Firewall Manager to then control multiple endpoints across your entire organization so you can have consistent policy. Remember, AWS takes care of the patching. They take care of the maintenance. You don't need to worry about any of that. It's all part of the service. A closer look at some of the more fine-grained features here in a modern firewall that AWS Network Firewall is. You get things like domain filtering, Suricata-compatible rule sets, IPS, IDS functionality, but also you're going to get visibility, meaning you're going to see all of the flow logs if you want, all of your rules and alerts can get piped into CloudWatch, Kinesis, S3, and then the possibilities are endless there, how you want to visualize or report or do threat hunting inside of that data. What are some of the use cases we see? Well, the first swim lane you see there is the one you're probably here to listen. That is egress security. And Kevin and our folks here from Robinhood are going to go into that deeper. Also, we have east-west protection. So VPC to VPC protection. Network Firewall helps you there. And also, again, the IDS and IPS functionality is built right in. So I'm going to hand things off now to Houston.
All right. Thank you, Graham.
Sorry, Kevin.
Hi, I'm Houston Hopkins. I work on the Robinhood security team along with my co-presenter here, Kevin. We're delighted to be here today to talk to you a little bit about our network firewall journey, which actually started a little less than a year ago. We're looking for ways to really aggregate and dig deep into our egress controls, as well as get better visibility on aggregate of everything that was happening inside of Robinhood. So to speak about the problem, so there was generally our egress controls were tightly coupled with the applications that we run. That's like we use security groups, we use NACLs, and we love those things. However, we needed an aggregate view. So if perhaps there was a control that was missed, or we wanted to see what egress traffic was still being allowed, we needed something deeper. We needed something that would complement our current cloud capabilities, so something we're familiar with. And we like the guardrail approach, so ways to get a lot of value early on and then get really deep later. Most importantly, we didn't want to break production, and we wanted to keep our engineers happy. So what we were looking for. Most importantly, it's egress control. So we were looking at north-south traffic going up and out to the internet. That was the primary thing we were looking for. We needed a flexible rules engine. I think that's mentioned several times in what Graham just said, but the flexible rules engine made a big difference for us. We needed something we could use, something we could implement. We were interested in deep packet inspection and packet inspection in general, what we could do there to inspect TLS, SNI, et cetera, which actually, we needed something to see domains. We needed it to be reliable. We trust AWS to be reliable. We're excited about the cellular architecture. We were familiar with it from other AWS products that we used. And we enjoyed the fact that there was a managed portion of this infrastructure to keep it up and running, but also managed rule sets that we could learn from, use, and adopt. Finally, it needed to be scalable. We mentioned pay-as-you-go several times. We like to build things up as fast as we tear them down if we need to, with very little overhead to not do that. And we use infrastructure as code, so we needed something that worked in Terraform, which is what we use. So you may be asking, do I need a network firewall? I can't exactly answer that question for you, but I can give you a little bit about how we went about this. So if you look on the right, there's traditional VPC controls, and they're great. We don't plan to replace them. They're not going anywhere. But we did need something that was more of an aggregate view. So the things to really focus in here, there's a lot of text on this one, is domain level filtering. We needed something to see domain names, DNS names. We also liked that the quotas and service limits were clearly documented. We had a great idea on how we wanted to build it, where it would scale. And we like the managed capabilities, of course. So this is our approach, and it's quite simple in the beginning. Let's get those firewalls deployed. Then we're going to implement some telemetry to see what we're learning and analyze that data, put them into dashboards and see what we find. And surprise, we found things very early on, very, very nice areas for improvement. Secondly, we really had to focus on blocking and tackling. As we, now that we have this capability, we needed to know how and when to use it effectively. We needed people to know how to react when we had an emergency, and who were going to be in those approval chains. I say do this early before you need it. Finally, as we progress on, and we're still on this journey, denying known bad is great. It's a great first place to start. But mine your data to learn how to build an allow list and look more towards a positive security model. And there will be things that don't fit in your positive security model. This helps us identify better ways to isolate that traffic. In short, it's really helping us keep tabs on our quest to have a really great data perimeter. At this point, I'm going to hand it off to Kevin.
Thank you. Hello, once again. My name is Kevin Park, and I'm a security software engineer at Robinhood. I had the opportunity to implement data plane of the AWS Network Firewall at Robinhood throughout various environments for the purpose of egress control. And I'm here to provide some guidance, share technical details, and including easy mistakes I've learned throughout the process of implementing AWS Network Firewall. And the best part is that I was able to insert the firewall into the live production environment with zero downtime. Before diving in, I want to share some of the implementation goals that we sought out to achieve with the network firewall. First, we want to capture and monitor all egress traffic. By egress traffic, we mean any network traffic that originates within the Robinhood's internal environment and traverses out to the public internet. We not only want to see which IP addresses it's reaching out to, which port, but also be provided with useful information that can aid us in implementing proactive controls and hopefully help us in the investigations down the road if necessary. And second, if we have a bad traffic, we want to be able to block immediately. But most importantly, firewall must not introduce any new bottlenecks in the production environment that the engineers now have to deal with. Now, we want the firewall to be completely transparent for those engineers who build, test, and deploy the services. But I also do want to explicitly mention that we are here to capture and monitor all the egress traffic, but not necessarily all the ingress traffic. So if you see any diagrams down the road where you go, that does not capture all the ingress coming into the Robinhood system, this is the reason why. Let's go over the couple of high-level options that we explore in the high level. First is the centralized model. In here, we have AWS Transit Gateway and a security VPC in the right. Security VPC is where we host the one network firewall and has the NAT gateway going to the internet gateway. So if we have one or more VPC instances, all of them would connect through the transit gateway, through the TGWENI, and route to the firewall and to the public internet. Now, the benefit of this is that it's one single firewall deployment. Now, this comes with the benefit that it's a single point of management with, and since it's one firewall, you only have to deploy firewall rules to this single one, and for smaller companies, that's a bonus if you don't have a high traffic going through and you can route multiple environments, VPCs, to this one single firewall. But at the same time, this can be a downside if you want a little more reliability. This becomes a single choke point. So if you have a misconfiguration in the transit gateway while maintaining it, this can become a single point of failure where it can impact all the VPCs that are routing through this one single network firewall. Now, the second option is the distributed model. In this model, the firewall is deployed in place where the infrastructure already exists. In the example here, we have two Kubernetes cluster in a VPC spanning across two availability zones. In here, there are 4 total NAT gateways, 2 for each cluster and for 1 each availability zone. And for that each NAT gateway, there is a network firewall endpoint paired with it, giving us a 1-to-1 scaling. And with this distributed model, you will have multiple firewalls, in which you can do a phased rollout of the firewall rules. And so if you want to test the firewall rule in the development environment first, you can roll it out and then roll it out to production. Or if you have multiple clusters in the production environment, you can test it out in one smaller production cluster first and then gradually roll it out to the next ones, more bigger ones. Now, the downside is that, obviously, this has n number of firewalls. So if you have n number of firewalls corresponding to n number of environments. So if you have 5 Kubernetes cluster in a VPC and 2 in other, that means that you'll have to deal and manage 7 total firewalls. So if you're more of a smaller company, this might not be the approach, as you might need a playbook, automation to make sure that you have all the firewall rules that you want in place and you're not missing in one or the other, because you can lose track of it as the number of firewalls grow. But for Robinhood, we decided to go with the distributed model. The reasoning behind is primarily scaling needs. NAT gateway has a max throughput of 45 gigabits per second, and each network firewall endpoint has a max throughput of 100 gigabits per second. Here at Robinhood, we almost maxed out 45 gigabits per second NAT gateway limit when we had multiple production clusters sharing a single NAT gateway per AZ, of course. Now, because of that, we have split out the NAT gateways to each Kubernetes cluster. And with the firewall deployment, we don't want to introduce that kind of similar bottleneck, so it was obvious that we wanted to go with the distributed model. But for, obviously, as I said, for smaller companies, centralized model might be a better fit. Before going into how we deployed the network firewall, I have to show you guys the before picture. So this is an example of a Kubernetes cluster spanning across two availability zones, US East 1A and US East 1B. And at the bottom, those are the route tables that is associated with the public and the private subnets. And the green ones are the public subnets. It consists of a NAT gateway per AZ, of course, and public load balancers. And on the blue, on the right side, the blue ones are the private subnets, which consist of Kubernetes nodes, which are just made out of Amazon EC2 instances. There's some key details I want you guys remember is that on the public subnets, the NAT gateway and public load balancer share a same subnet. The reasoning I'm telling you to remember is that I'll show you how you can make a simple, easy routing mistake because of this. And just going over a simple route table, in the public subnet, it's routing directly to the IGW, whereas in the private subnets, it's going through the NAT gateway in the public subnet, then to the internet gateway. Now, from that, how we decided how we deployed the network firewall. We inserted the network firewall endpoint into each AZ by creating a dedicated subnet for the network firewall and have it sandwiched between the public and private subnets. Now, the reasoning we put it in there is that we want to be able to see all the egress traffic, since that's our goal. So we want to be able to capture it going from the Kubernetes nodes to the NAT gateway and to the internet. Now, due to the NAT gateways and the load balancer sharing a subnet, firewall system between the public and private subnets, which means that we will occasionally capture some internal-to-internal traffic, primarily because public load balancers reaching into the Kubernetes nodes will be the internal-to-internal traffic. But that's okay because the firewall endpoint has a much higher throughput, up to 100 gigabits per second, so we have the buffer room we need. But if our goal is to primarily just capture all the egress traffic, why not place it after the NAT gateway before the internet gateway? Now, this would capture all the egress traffic that we need. However, and it would make the routing table much simpler. However, placing it after the NAT gateway would mask all the Kubernetes, like the source IP addresses. And for the purpose of firewall, we want to be able to see where it's coming from internally, not just the NAT gateway that it's coming from. But one thing that you need to be very careful when designing the route table is that you have to preserve the network symmetry. So if you have a traffic going through the firewall in one direction, then you have to make sure that the return traffic is also going through the network firewall. If you have a traffic going through the firewall in one direction, but not in the other direction, going around it, firewall will notice it and simply silently drop the packet. And if you deploy it as it is, you'll have a bad day. You'll have a production outage. And yeah, you don't want that. So how did we fix it? Oh, actually, let me first mention this. So this example right here is an actually mistake I made while designing it. Because I was so focused on making sure capturing the egress traffic going through the NAT gateway, I forgot to consider the public load balancer in the equation of the public subnets. So in this route table, I have the VPC CIDR in the public subnet pointing to the network firewall endpoint. So in the public subnet route table. And in the private subnet route table, we have the 0.0.0/0 pointing to the network firewall endpoint. Obviously, this works for the NAT gateway and the private subnets, but this creates a network asymmetry between the public load balancers and the Kubernetes nodes, and you can have a partial outage. Now, how do you fix it? Solution is quite simple as it sounds. You just introduce more granular routes. Rather than the VPC CIDR pointing to /16 pointing to the network firewall endpoint, instead you just define the exact subnet CIDR that you want to route through the network firewall. So in this case, public subnets route table will have 3 additional routes where these are the private subnet CIDR range in the same availability zone pointing to the network firewall. And for the same thing, private subnets will have public subnet CIDR in the route table pointing to the network firewall. Now this will achieve network symmetry for both the NAT gateway between the private subnets and the network load balancers. Now we have the architecture defined. Now, how do we deploy this systematically? Robinhood has obviously a lot of environments, and we want to be able to do this same thing over and over again without mistakes. To do that, we used Terraform. We use Terraform widely across Robinhood already, so it was a no-brainer just to use this and to deploy the firewall. And the way I did it, I just created a single overall overarching network firewall Terraform module that will do this for me. So this firewall module will automatically create the subnets for the firewall endpoints and the firewall, obviously, and the new route tables for the public, private, and the firewall subnets, and propagate with the proper routes, routing through the NAT gateway and through the firewall, and also configure logging and where to send those logs to. In addition, I also added a bonus of just the firewall-enabled Boolean flag, just true and false, so I can just set that to true or false to whether to create it or not in the VPC environment or the Kubernetes cluster environment. So because network firewall is pay for what you use, so if you don't want to create a firewall in such a small test environment that you're going to keep it internal, you don't need a firewall, and so you can just have that flag to have it or not. But one thing to note is that why am I creating a new set of route tables for both public and private subnets? As I mentioned, this environment already exists, but I'm creating a new set of route tables for the public and private subnet rather than just modifying the existing ones. Well, I duplicate the route tables. It's because, first, inserting a firewall into a live production system is tricky. As I shown in the example, one mistake in the route can bring the production down, have a partial outage or a full. How did I solve this? Is that I create all the necessary firewall-related resources in advance. This is including the route tables, and duplicate all the routes in the route tables, and add the additional firewall integration routes. This allows us to verify the routes once more and all the components necessarily before taking the system live. And then once we verify it and everything's correct through eyes or through a script programmatically, I have another Boolean variable called firewall route enabled, which you can set it to true and just do a single Terraform apply. This will switch the route table associations for the public and private subnets to the newly duplicated route tables in instant. Now, this is the trick that I used to bring the firewall live with 0 downtime. And we also replicated it today.
Quick note on that is when you're troubleshooting and you want to remove the firewall from the equation, it's a quick way to turn it off and turn it back on when you've made everybody happy that it's not your fault. So.
Yeah, and on that note, this Boolean variable, the firewall route enable, also doubles as a fail-safe flag. So imagine a rare outage scenario where the AWS shared cell hosting the network firewall endpoint has a disruption, goes down. Now we can use that same firewall route enable flag, set it to false, and do a single Terraform apply again, and this will flip the route table association back to the original, with obviously in a matter of seconds. Now, but you might also be wondering, like, how do we make sure that the route tables that's not being used has the routes being maintained? The way I did it is this Terraform, since it's an infrastructure as code, I just have it set so that if you try to add a route to one of them, then it'll automatically add it to the other. So it'll always maintain its congruence, even if it's not being used. It's just that one has a additional firewall routes integration added to it. Now, moving on to monitoring and alerting. Like, deployment is the first part of it, but keeping it up and running is the second part of it, and continuous part of it. Now, firewall, AWS CloudWatch provides all the necessary operational metrics from the network firewall, and from that, we have two very important alert generated from it. And the first one is just a basic low firewall traffic alert. This fires if there's close to zero network traffic going through the firewall. This can happen if the firewall is just simply disabled or an engineer accidentally or deliberately disabled the firewall to bypass the egress control mechanism. If that happens, this alert fires. And the second one, which is even more important, is the firewall drop packets warning. This can happen this triggers when there are packets being actively dropped by the firewall. This can occur if the firewall endpoint is hitting the bandwidth limits, which is pretty unlikely because it has 100 gigabits per second throughput, way more than double the NAT gateway, so this is unlikely. And the second scenario is there's some firewall rule that is being triggered to drop the packets. Usually this will mean that scenario because usually you have the firewall rule to drop packets if it's like a malicious traffic. So if this fires, we will get an alert on Slack just as above, but also be paged on our phones directly because we would want to hop in and investigate right away. And then on to logging and visibility. So on the example here is just an event that I pulled from a network firewall. And here, obviously, you can see the fields that would be present in the average VPC flow logs. You see source IP, source port, destination IP, and destination port. Like, this is all useful. This already comes from flow log. But what makes the network firewall logs different is that it comes with like additional information like TLS fingerprint, like SNI domain version, domain, and the TLS version. And in other cases, it also comes with like JAW3, like fingerprint hashes, where you can reverse stack rank to find like the outliers and be like a threat hunting exercise and start investigation from there. And I'll be handing off to Houston to provide more insight.
Yep, sure. Thanks, Kevin. Just a quick note, I know I mentioned dashboards a few slides ago. Kevin's overwhelmed us with awesome material since then. So this is just a quick, it's really a mock-up of one of our early dashboards showing what we got immediate visibility on by looking at domains, which was a nice added feature of using the network firewall. And a couple of things that we looked at right away. So first of all, how often was Robinhood talking to AWS through the internet? That's pretty interesting data. When you're building data perimeters, you like to use things like VPC endpoints. So did we have gaps where we needed better coverage? Yes, we did. So the other thing is, how often is Robinhood going out to the internet to talk to itself? So do we have a lot of opportunity to build in or just some opportunities to build in better routing there, maybe route to the internal load balancer instead of going back out to the internet through all the various layers to come right back in. But more typically, we did actually look at all of the different domains that we were reaching out to, right? And so there's various egress controls all the way up the stack. So there's certain domains that were showing up repeatedly, and were those interesting? That helps us build our allow list, our quest for being positive security. Likewise, so you'll see maybe tons of hits to certain things. You're like, oh, those look like valid services. I hope we use those. If those look suspicious, we hopefully, we would investigate those immediately as well. But then we also go down to the bottom. What is rare? What are these random sites that were random domains that we hit on occasion? What ports are being used on those domains? Are they interesting? And what we found here is you'll find an application, I think this is pretty common across many companies, someone built a scraper, right? Let's scrape the news. We're Robinhood. We're interested in what's going on in the world. So a news scraper, or maybe a threat intelligence scraper. Those types of things are really hard to wrap egress controls around because you want them to see the internet. Those are great opportunities for moving that infrastructure to its own unique place and not applying the same exact rules that you were for the rest of the environments. I often, here, I'll touch on this here. Maybe. All right. So those discoveries, I just accidentally let the cat out of the bag before I got here. But we quickly identified opportunities where VPC endpoints were not in the right flows. So we had a lot of opportunity to increase that and reduce our internet traffic. It's always good when your security control makes friends with your cost controls. It's nice to have them hand in hand. And then likewise with the Robinhood traffic that was routing directly to the internet and then coming right back in the door, lots of opportunity to save some money there. And as security people, if it doesn't have to go to the internet, we don't want it to go to the internet. And then I say measure the top and the bottom. So again, if you have a lot of domains you're hitting all the time, you should know what those are. That should look fairly stable over time. If you have domains that are just really random and rare, those should be interesting to you as well because if you're building an allow list, why would someone randomly hit these domains? There's good reasons, but you need to know them. This gave us the visibility to really investigate that. And also, I mentioned here, is there a middle? Sometimes you get so excited by what you see what are we hitting all the time? What are we rarely hitting that you may miss some things in the middle? It's worth it to look all the way up and down. Those domains can easily be evaluated for against various threat intelligence services feeds, you name it, domain reputation sites. And if there's anything interesting there, it's worth investigating. And again, on the deeper segmentation opportunities. If there's things that don't fit, it's best to just try to find a place to move those snowflakes to. Back over to Kevin.
Yeah. I want to add a thing. One of the interesting discovery that we didn't expect was in the cost savings area. We would have expected AWS Network Firewall to add cost to our bills, but it provided more cost saving opportunities because Network Firewall provides TLS SNI domains. So even if it's reaching out to the AWS services, since we can see the domain names that it is reaching out to, we were able to see that there's this huge S3 traffic that is reaching out through the NAT gateway, which instead of the NAT gateway, we can use a S3 VPC endpoint to save significant amount of money. And through this, we were able to save some quite significant amount of money on there. This is not only just to S3, but also DynamoDB, which also has a S3 VPC, which has its own VPCE. And on the right, to wrap it up, I want to add further improvements we can do in the architecture of the firewall. Now, I said to have a network symmetry between the public and the private subnets, you need to have more granular routes. Now, if you're one of those people that you like having nice, simple route tables like me, and you don't want to have a bloating in the route tables, if you have a lot of subnets, this is the way to go. You want to separate out the NAT gateway into its own segmented subnet, then you can have a more flexibility over the route table where you only route traffic between the NAT gateway and the private subnets through the network firewall endpoint. And all the public load balancer and traffic outside the firewall, around the firewall, directly to the private subnets, to the K8s nodes. Now, this has benefits. Obviously, I mentioned simpler route tables here as shown. You no longer have that bloating, but also you can have, you will no longer capture the internal-to-internal traffic that was adding noise to our logging capabilities and just simply focused on the egress control. Now, also, by eliminating those internal-to-internal traffic, this does additionally save some of the cost because network firewall is built on which amount you use. Now, you can also do this with zero production downtime if you're spanning across multiple availability zones, and you can introduce a temporarily cross AZ traffic. The trick is that, so if you have another AZ, you just simply route the internet traffic to another NAT gateway in that AZ. So introduce that cross AZ traffic, delete the NAT gateway that you want to move it out, but preserve the elastic IP and create a new subnet and create a new NAT gateway with the same elastic IP that you preserve. Now this way, you are preserving the egress IP, like the public IP that is egressing out to, let's say if you have some IP address-based filtering for other external services, then you can do that. And finally, obviously, just move the internet traffic back to the new NAT gateway. Now, this way, you can, if you already have NAT gateway and other services within the public subnet, like Robinhood did, you can simply move it out in this scenario. But yeah, thank you. We're